Okay, so we're talking about regularization. And today I want to finish the discussion of regularization and see if we can talk a little bit about other stuff. We'll see depending on how far we go. I'll tell you what I will talk about next, but let's get going with the. So we introduced this idea that you can use, for example, feature map to do nonlinear versions of logistic regression or regression. I'm going to come back to this idea maybe when I show you some demo, but today let's start with where we left off in terms of regularization. We were looking at the ridge regression, okay, and here I'm assuming that the features are xi. They could be like after we map it using a feature map to a bigger space. So there's really no loss of generality if you think about linear regression after you transform your variables to a new feature space. So now you can actually model nonlinear functions in the original state. Okay, so in any case, so we're dealing with linear regression, and we added this L2 penalty here, and this is called a regularization parameter, and this procedure of adding a penalty to control the parameter to the the empirical risk or the loss function is one way of performing regularization. So we want to see what effect it has on the estimator. And so we started with a true model in which the expectation of y given x is actually a linear function of x. The parameter is theta star. I'm going to assume the variance of the noise given x is sigma squared. And so now I have yi's training data that are drawn from this model. So we generate the data according to this true model. And I can write this in matrix vector form by introducing this vector y, matrix x, vector epsilon. And so you get y equal x theta star plus epsilon. That's your true model. And then I can write the ridge regression estimator in a similar fashion. So if you manipulate this objective function, you can write it in this form. And you would take the derivative, so equal to 0. This is a convex function. And because of this term, you can actually verify it's strongly convex. So it has a unique global minimum. So the only thing that we have to do is find it. And because the optimization is unconstrained, at the minimum, we have to have the derivative vanish. So the derivative has to be 0, or the gradient has to be 0. And so we take the gradient, say equal to 0. And the end result is that we have this one way to represent theta hat lambda, the solution of the regression optimization problem. Okay, so the solution is in terms of theta. So that's an estimate of the true theta, theta star. And I also mentioned that the way I wrote this, these have meanings if you think of xi's as being 0 mean, coming from a distribution. This is going to be the sample covariance matrix. And you'll show in your Horry problems that it's an unbiased estimator of the covariance matrix. And this is going to be a sample cross covariance matrix. So you can write it in terms of these matrices. This is going to be a vector. This is going to be a matrix. Okay. Questions so far? This is like a recap. And then we, instead of comparing theta hat to theta star, we decided to compare f hat to f star. So remember that we're trying to predict y. And so this is the So this is going to be our optimal predictor, if you remember, f a star. So if my model is like this, the optimal predictor, the optimal rule under the quadratic laws would be the conditional expectation of y given x, which is exactly this theta star transpose x. So that's the true function. There's a function of x. And so my estimate would be like theta hat transpose x. So that would be my estimate of the true function. So now I'm going to compare the two functions here. So these are like regression functions, and one the true one, the other the estimated one, and I'm going to compare them using this norm. So this norm is sometimes called the empirical norm. So empirical L2 norm. L2 norm. And so this is like a weighted average of these deviations between the f hat and f star on the training data. So this is okay. So some people might be worried that we're evaluating things on the training data. You might be like overfitting stuff like that. This is not as much of a problem because I'm comparing the true to the true function, not on the observations. Okay. In practice, you don't have the true function. If you go back to some of the earlier discussions, this quantity is going to be very close to the generalization error or the risk up to a factor, which is like up to a term which is related to the Bayes error, which in this case would be sigma squared. But in any case, I'm going to look at this. And what I'm going to do is I'm going to look at, so this is going to be a random quantity because the path is random. I'm going to take an average, but I'm going to average over the conditional randomness of yi's given xi's. Okay. So this notation that I had used before, this is my way of writing conditional expectation given x1 up to xn. So x1 up to xn are in this case, we write it as small. So these are the training x's. Okay. And when I write things like this, what I really mean is take expectation conditional on, or with respect to like y1 up to yn, conditional on x1 up to xn, basically. Or everything else conditional on x1 up to xn. So these training data will have some variation, which is caused by the noise, not by varying x. So if I let the x's vary, there's some variation due to the fact that x's will also be randomly selected. But I'm going to condition on the training x's and then average out the variance. Basically, what I'm going to average is this these conditional variances or these conditional distributions, basically noise given x. So I'm gonna like average over this noise, not over the x's. Okay, so that's what I want to calculate. That's like the expectation conditional on the training x's of this guy, and this turns out to have a closed form solution. And then we can study how the regularization effect, like what does the regularization do? Okay, that's the goal. Sounds good. So how do we do this? So we had theta hat lambda was x transpose x over n plus lambda I inverse x transpose y over n. Should I do this? So let me introduce, I'm going to introduce a sampling operator. This is going to be helpful at some point. But what I'm going to introduce is that this operator that takes a function and writes psi of f, takes a function and produces this vector, which is rescaled version of its values at x1 up to xn. So I evaluate the function at the training data, rescale it. So call this the sampling operator. Sampling operator. So it produces what? Like an approximation of the function as a vector. So just evaluated a bunch of points. And what I noticed is, by the way we constructed it, that the L2 norm of this f, like this psi of f, the usual L2 norm as a vector, would be 1 over n summation I from 1 to n fxi squared, which I call the like empirical norm of this function. So the empirical norm of the function is really the L2 norm of this sampling operator applied to f. Okay, and so if the function looks like, suppose f of x looks like a linear function. Okay, if f is a linear function, then psi of f would be 1 over root n. I'm going to write it as well as, like you can write it as well as x transpose theta. So they're the same. x1 transpose theta up to xn transpose theta. So can I simplify this expression or what it is? So remember the x, there's the design matrix, which is n by d. So this is n by d. And I simplify, I like write it compactly in terms of the design matrix. If you go back to your notes, you would see that yes, indeed, we can do that. And so it would be like this. So we 1 over root n x times theta. Does that make sense? So if you go back, we did this last time for, so remember writing something like this as that, okay? Basically, we're doing this part. Okay. So what this idea, like what this is saying is that the sampling operator applied to these linear functions behave nicely. So for example, if I do psi of f star, that would give me 1 over root n x theta star, because that's a linear function based on theta star. And if I do psi of f hat, this would be 1 over root n x theta hat lambda. Okay, f star was theta star transpose x. F hat was, let's say f hat lambda is theta hat lambda, that's the ridge regression estimator times x. So I get that. And so what I want is f star minus f hat in empirical L2, which we showed actually, I have to argue as well that psi is a linear function. So, so this is going to be psi applied to f star minus f hat squared. That's by this argument. So imagine there's a g here, or any f. So this applied to any f. This works for any f. Now I'm applying it to the deviation of f star and f hat. So this is true, right? And then I argue very easily, you can argue that this sort of is that minus this guy. No, actually, I don't, yeah. I don't actually really need to do that. You can also see that f star x minus f hat lambda x, this is also a linear function, but it would look like this transpose times x. So really, this is going to be 1 over root n x times theta star minus theta hat lambda squared. Either you say that this is linear, so you get psi of this minus psi of that, and those are like that. Or you can just realize that the difference is another linear function with a different theta here. And so psi of it is just something like this. Any question? That makes sense. So yeah, but I would like to look at probably this version. Just flip the sign. So 1 over root n comes out. I get x, flipping the sign doesn't change things. So that's the basic like argument that I can write this empirical norm in this fashion. Okay. Another way of looking at things is that this is just the samples of the function, the estimated function at points 1 over n and then rescale. This is really x lambda hat. So really what I need to study is this guy or this part. So if you've seen like usual statistic, this has a name without the 1 over root n. What does this, like in regression terminology, x theta hat lambda or this guy? What do you call this? It's like 100C version of. Any guess? I'm gonna like copy this. So that's called the fitted values. It's usually all the things that are in the regression line. This collects the vector. No, sorry, this one collects the vector fitted values. So what I need to study is this. Let me ask you if you have any questions. Okay. It's not particularly difficult, these things. So I'm going to look at this. If you look at this, you'd see that, okay, 1 over root n here. I get 1 over root n x transpose x over n plus lambda I inverse x transpose y over n. Okay. And so I'm now going to define this matrix h lambda e 1 over root n x x transpose x over n plus lambda I inverse x transpose over root n. So this only depends on the x matrix. So I define something like that, depends on lambda as well. So with that, I can rewrite this as 1 over, no, yeah. So I'll take 1 over these root n's out. Okay, so I get, you see this part is h lambda. So what I would get here is really h lambda times y over root n. So a simple formula. What I'm looking at is this matrix times y over root n. So does this look familiar to people? Sort of from 100C. Let's say if lambda is 0, have you seen something like this? How many people have taken 100C? 0. Okay. 1. Did you recall from
Without the hat matrix.
hat? Yeah, great. So if lambda is 0, the n comes out, flips, then it cancels those out. So h is 0. So like that would be the regular OLS basically without regression. So h would be like x transpose x inverse x transpose. So this is 0, then like this is flipped. So 1 over n would be n, and then cancels the root n's here. So you get that. So it's called the hat matrix in regression. And this is roughly saying that the vector of fitted values of the hat matrix times the observation that you'd see in like 1 and C. So what are the properties of the hat matrix? Mathematically.
Is it idempotent?
Idempotent. It's a projection, like orthogonal projection matrix. Orthogonal projection matrix, which means that it's symmetric and idempotent. So it's equivalent to being symmetric and idempotent. What does it mean to be idempotent?
Matrix by itself.
Yeah, multiplied by itself, you get itself. These are projection matrices like that. So if you project something and then project it again, you get the same thing. But this guy is not a projection matrix. For any lambda other than 0, it's like a perturbation of this projection matrix. But in any case, it's like the formula is very similar. So fitted values is like this matrix times the observation, if you ignore the 1 over root n. Sounds good so far. A lot of like calculations to get to this point. But if I have this now use we use our generative model. I use our generative model, so y is x theta star plus epsilon, if you remember. I'm going to plug this into this, so I get 1 over root n x theta at lambda is hy times x theta star plus epsilon divided by root n. If you rearrange, you get h lambda x theta star divided by root n plus h lambda epsilon over root n. Just expand. Okay, we just plugged in this is from the way we generate the model. Remember, this part, we are assuming that y is generated from a true model like this, and you rearrange, you get something like that. So you're plugging that in. So these are vectors. So this contains all the y1 up to yn. Remember, this contains like epsilon 1 up to epsilon n, so on. So now what I want, if you remember this identity here, I want to subtract x minus theta star as well. So I'm going to subtract 1 over root n x theta star from both sides. I get 1 over root n x theta at lambda minus theta star. The other side I get, let me do it step by step. Minus 1 over root n x theta star from this side. The other side would be h lambda x theta star over root n. I'm going to put minus 1 over root n x theta star here plus h lambda epsilon over root n. So I just added this to the both sides. Now I'm going to combine these two terms. I get I minus h lambda times x theta star over root n. And here I would get 1 over root n x theta hat lambda minus theta star. And then I have the other noise term. Okay. So identity minus lambda. Does this make sense to people? So if you multiply this out, this gets multiplied by identity, you get that. Or the other way around. Okay, sorry. Yeah, I should have written it the other way around. That's like, this would be negative. Negative of this. Sounds good. It should sound good. Haven't done much. Now, I'm going to use this result, right? So f hat lambda minus. So use, let's say, double star. Use double star. So this is going to be exactly what I had here, root n. So this is empirical norm. This is what we showed is that this is x theta hat lambda minus theta star, and then a square. So I'm going to put an expectation tilde, right? And yeah. So now this is going to be expectation tilde, just this guy that I have there, minus I minus h lambda x theta squared over root n plus h lambda epsilon over root n. Okay, then I have to expand this and take expectation. I will assign this as a homework problem so that you can figure this out for yourself. If you expand, you get this guy norm squared plus this guy norm x squared plus twice the inner product. So it's like having a, let's say, plus b squared is norm a squared plus twice inner product of ab plus b squared. Okay, this is like a transpose b. In this take expectation, and somehow you have to argue that this turns out to be like the cross term vanishes, and then I get something which looks like this. So this gets us the expectation of the first term. The first term is constant, so the first term is squared, the sign goes away, so I get I minus h lambda squared, like x theta star over root n squared plus expectation of the second term is squared. Lambda epsilon over root n squared. Okay. You have to argue this for yourself. The first term is squared. This is the first term is not random. The second term is random because of this. And once the dust settles, you would see that this is going to be the result. And this is what you're going to show. Okay. Questions? Yeah, let me try to see. So what next? So this term is going to be called, so this is a kind of decomposition that sort of you've seen before. Anyone knows what the name of the, like a something trade-off, or anyone what these two terms mean?
Bias variance.
Great. So this would be the bias term, and this would be the variance, right? And it's not hard to see that if lambda is 0, so if lambda is 0, you would get this H naught here. So you get this projection matrix. And so if lambda is 0, this I minus O lambda equals 0, then I minus H lambda would be I minus H naught. So that bias term, something interesting happens to it. So anyone knows what happens? I forgot if I assigned this the whole problem, but anyone knows what this would be in that case? So H0 or H naught is the projection matrix projecting onto the column span of X. I minus H naught projects onto the complementary subspace. There is a very simple answer to this. Can you guess? What is the simplest answer? So if lambda is 0, this would be the OLS. What do you know about the bias of the OLS? It's actually biased for the regression function. So this turns out to be 0. Okay. If lambda is 0, this would be 0, so there would be no bias. like pure variance. So this is sort of the like version of the MSE. It's like proportional, like not proportional, it's up to like to sigma squared, the same as the MSE. But that sort of a result would show this. But it's interesting that if lambda is not 0, then that bias term is there. So it's going to be there. And you can change, by changing lambda, you can trade off the bias and variance, as we'll see. Okay. Questions? So let me try to simplify the variance a bit. The variance is this guy, like the variance term. So it's like 1 over n expectation of h lambda epsilon squared. So anyone knows how to deal with something like that? How do we calculate something like this? So epsilon is a vector. The conditional on x1 up to like xn. So epsilon is basically a vector number. Epsilon is epsilon1 up to epsilon n. These are the noises in y's, right? So yi is x I transpose theta star plus epsilon. And so given x1 up to xn, which is what we're conditioning on, this would be normal, which mean 0, and covariance, which is like sigma squared all the way on the diagonal 0 elsewhere. So it would be normal, which means 0, covariance matrix sigma squared I. Okay. Right. So how do we deal with this? Anyone seen something like this and wanted to see? Okay, I'm gonna do it, but I don't want to spend too much time on it. There's a trick here. So we write this like that, transpose times h lambda epsilon. Okay, so the norm squared can be written as something like this. It's like saying a squared is a transpose a. And what does the transpose do to a product? Flips. You get epsilon transpose, h lambda transpose, and I can drop the parentheses because of the associativity rule of matrix product. So I get something like that. It's not hard to see that h lambda is a symmetric matrix. So the way we defined it, if you look closely at it, if you transpose it by the flip, by the fact that transposes flip the order, so you have to transpose from the I don't know, my right-hand side and your right-hand side all the way, and then you flip everything. So you get x transpose transpose, you put it first, you get the same thing. And then the middle guy is also symmetric. So it's a symmetric matrix. So this is really going to be h lambda. And so you get epsilon transpose h lambda squared epsilon. Okay. So what is the next trick that we have to use here? Anyone knows the trick? It involves the trace of a matrix. What is the trace of a matrix? So diagonals. So if I have, this is a scalar quantity. So this is like n by 1. This is n by n. This is n by 1. So this whole thing is 1 by 1. This is really a scalar, as you'd expect, because it's the norm of something. So this is going to be equal to its trace. it's a matrix, 1 by 1 matrix. So the sum of the diagonals are just, there's one diagonal, which is, so this is the trick. Write it like that. Then what can I do? Trace has this property, which I can do symmetric permutation of the elements. So for example, trace of A, B, C, if these are matrices, is the same as trace. I can move A to the other side. Just circular shift. I can move B to the other side. And if you move C to the, like, it would be this. So just circularly shift. So move A to the end and then B to the end. These are all equal. So there's a property of trace. I'm going to move the first element to the last position. Okay. So now this is interesting because now both this and this are matrices. So this is a non-trivial business here, but the trace is going to remain the same. So if you haven't seen, this trick is very useful. So what I end up having shown is that h lambda epsilon over root n norm squared is equal to 1 over n expectation this trace. So why did I introduce the trace? Because trace is a linear operator. And anyone can tell me what comes next? Trace is linear, a linear operator. So because expectation sort of moves past like linear operations, I can commutes with linear operators. I can exchange the order of expectation and trace. That's the reason why I introduced that trick. So if you haven't seen this, it might be a little bit mysterious, but once you do it enough, it becomes easy. So trace and expectation. So I do this like in great detail, probably in more detail, not great detail, more detail in 100C, but this is going to take a while, but just hopefully like you see it once, you remember it maybe next time. Expectation is a linear operator, trace is a linear operator, they commute, so you can order it, they reorder them. Now, this is another 100C like fact. So what can I do next? So h lambda squared is deterministic, epsilon transpose is random. I'm taking the expectation of this matrix product. What is going to be my next move?
Outside.
What outside? Great. So this comes out because again, by linearity, like expectation is a linear operator, and then matrix multiplication is linear. So this goes in. So what is this? It's not zero, it's epsilon transpose. So epsilon transpose is really like epsilon 1 squared, epsilon 1, 2, epsilon 1. So epsilon 1, epsilon 2, epsilon 1, epsilon 3. On the diagonal, it's going to be epsilon squared up to epsilon n squared, but off diagonals are epsilon I, epsilon j, basically. So the ith element of this is going to be epsilon I, epsilon j. It's an n by n matrix. So because it's zero mean, this is going to be the covariance matrix of epsilon. If you haven't seen this, hopefully you've seen it now. This is the covariance matrix. So the expectation of, you can see the diagonal would be the second expectation of epsilon 1 squared. It's going to be the variance of epsilon 1 squared because the mean is 0. And expectation of epsilon 1, epsilon 2 would be the covariance of epsilon 1, epsilon 2, because again, the mean is 0. So it would be a matrix whose diagonal elements are variances of the coordinates. Off diagonal elements are the covariance, pairwise covariances. So this is what the covariance matrix is. So in general, whatever the noise, this is like, I put a tilde here. This is conditional covariance of epsilon given the training x's. So we ended up with a nice formula. It's going to be the trace of h lambda times the covariance of epsilon. So if you have any like complicated noise, covariance matrix is still valid. But in our case, we have a very simple covariance structure because we assume that these training data are independent. The IID, you can see I already wrote it here, sigma squared I, because like individual elements of epsilon are from different iterations of like getting the samples for training. So the training samples are independent. So across I, we have independence, so the covariances go away. So these have the expectation here. So these covariances, it's a little bit difficult to write it here. So you get expectation of epsilon 1 squared, expectation of epsilon 1, epsilon 2, . So these guys would be 0. These guys would be sigma squared. So you get sigma squared 0 everywhere else. So it's just sigma squared I, conditional on the x's. And so this is really sigma squared I. And so sigma squared comes out, you get sigma squared over n, trace of h lambda squared. This is a very simple formula for the variance. Sounds good. We use a bunch of tricks, which if you haven't seen, it might be a little bit mysterious, but we took care of this term. And we're almost in a position to take care of the second term as well. So we have, let me copy paste this here. Okay. Okay. Now I reduce this to sigma squared over n, trace of h lambda. At this point, everything is sort of deterministic. You can actually plot this as a function of lambda, and you get the regularization curve. So this is some sort of an MSE, and this is a function of lambda. You can see what happens. But I want to go a little bit further. Is there any questions here? Just let me pause. Have this. Questions? So this is our sort of semi-final result. You can work with this. But I want to do a little bit of simplification and also introduce you to this idea of like simplification or simplifying using ESVD of 1 over root n. So SVD stands for singular value decomposition. So let me ask you if you guys have seen singular value decomposition. Anyone? SVD? Eigenvalue decomposition? Anyone remembers what singular value decomposition is? Should I look up SVD in Wikipedia or? Anyone has seen it? No. Doesn't look like it. Eigenvalue decomposition? Anyone? Eigenvalues, eigenvectors? Okay, it seems like eigenvalues and eigenvectors are familiar. So this is based on singular values and singular vectors. These are like equivalent like versions of eigenvalues and eigenvectors for the rectangular matrices. So this matrix N is N by D. It's not symmetric. So the natural thing to talk about is singular values. I'm not going to go into details of what it is, but the end result is very easy to remember. So it's a particular decomposition that makes X look like a diagonal matrix. Eigenvalue decomposition makes a symmetric matrix look like a diagonal matrix. SVD is the same thing, like similar thing for general rectangular matrices, and diagonal matrices are easier to work with. So what this is saying is every rectangular matrix has a decomposition which can be written as, like, this is N by, different ways of writing it, N by N, and then N by, in our case, N is big. So you get N by D, D is small, and then another D by D matrix here. So these are orthogonal matrices. This orthogonal matrix, this is another orthogonal matrix, and this is diagonal. But it's rectangular, so it's a little bit difficult to define diagonal. So there's non-zero elements here, and then the rest is zero. Okay, diagonal there, the rest is zero. The version, so orthogonal matrices, anyone knows what orthogonal matrices are? What are orthogonal matrices? If this is U, what properties does it have? It would have like columns that are normalized. Norm would be 1. Like each column would have norm 1, and the inner product of the columns would be 0. The columns would be orthogonal to each other. So the columns would be, these are called, I believe, left singular vectors of the matrix. The columns of this would be right singular vectors. These diagonal non-zero elements are going to be called like singular values. If, for example, if this is U, the column being like orthonormal, like is equivalent to saying U transpose is equal to U. So U transpose U is equal to U transpose equal to the identity. Okay, I'm not gonna spend too much time on this because I don't want this version. There's a different version which is called 10 SVD or reduced SVD. So because this part is going to be 0 completely, I'm just going to drop this N minus D part here. And then I'm just going to drop this part, which corresponds to that. So I end up with a version which is N by D. And D by D nice here, and D by D here. So now this is really a diagonal matrix. So this is I'm going to call this S. I'm going to call this U. I'm going to call this V transpose. So V would be N by D. The columns are still orthogonal to each other and normalized to have unit norm. So you would have U transpose U is equal to I, but because I dropped the rest, this is not going to be I. That's the difference between this and the other version. V is still going to be orthonormal. So it's orthogonal because it's like full like square matrix. So this is going to hold. And in particular, V inverse is going to be V transpose. This is a property of orthogonal matrices. So this is called thin SVD or reduced SVD. That's the version I'm going to use. In SVD or reduced SVD. So in the end, I have root NX, which is U S V transpose. This is the way you usually write it. And U and V and S are special matrices. U, the columns are orthonormal. What it means that the columns are orthogonal and normalized to have unit L2 norm. Similar for V, and S is diagonal. So I'm going to write S as diag SI. I'm going to write it like this, I in D. What this means is that it's a diagonal matrix S1, S2 up to SD. Okay, these are the singular values of the matrix. And what this is saying is sort of that X behaves like this diagonal matrix if you view it in the correct basis. If you choose the basis U for the output and basis V sort of for the input or V transpose, then this transformation looks like a diagonal matrix. After this, there's a lot of intuition behind this, but since this is not linear algebra, I'm not going to go into it, but you'd see how easy, like how much more simplified things become. So this you can do in any numerical linear algebra, or using any numerical linear algebra routine. And in particular, you can do it in R, you can do it in Torch, Python, anything that has a reasonable amount of linear algebra capabilities. So far, so good. This is one of the most important things you learn in this course. Okay. If you don't learn machine learning, learn this. It's going to be very useful. If you haven't seen it. Whenever you want to simplify things, this is always good. Look up SVD and read the Wikipedia page. But let's see how this simplifies. So for example, I can simplify this H matrix, which is very complicated. You'll see, so where we define this, where do we define? Like that was my H. You can see it involves a lots of like x's multiplied by each other and identity. If I plug in the SVD of x, this simplifies greatly. Let's see if I have. Okay, so I assigned this as a homework problem, so I'm gonna leave it to you guys, but this is gonna be the end result. So if I define gamma lambda, which is a diagonal matrix, so because imagine so H lambda is x root n I plus x transpose x over n. So you plug in the SVD of x, and this turns out to be equal to u gamma lambda u transpose. So what is gamma lambda? Gamma lambda is going to be s squared plus lambda I inverse another s. So if you compare this with the above, it looks like we're replacing x with s, sort of, and then x transpose with s. But S is a diagonal matrix, I is a diagonal matrix. This really is going to be diagonal. When you multiply diagonal matrices, as if you're multiplying a scalar. So it's going to be the diagonal of SI squared plus lambda SI, this inverse I in D, and then this is just going to be just SI squared divided by SI plus lambda. Okay. What this is saying is that this is really recharge the pencil now. Well, the idea is like everything simplifies. There's a lot of things reduced to calculating with the diagonal matrices. Does this make sense to people? You're going to show this in your work problem, why that is u lambda u transpose, sorry, gamma u transpose. But sort of it's like as if I'm replacing x once I do this transformation u transpose with a diagonal matrix. And in fact, that gamma lambda u transpose, because u has orthonormal columns, that's the eigenvalue composition of H as well. So you can read off the eigenvalues, these entries of gamma are the non-zero eigenvalues, and the u's are going to be like the eigenvectors. So what this means is S1 transpose divided by S1 plus lambda up to SD squared divided by SD squared plus lambda. Okay. Once you show this, you also can show that H squared is really gamma lambda squared U transpose H squared. And so gamma lambda, you just square all these entries. The square of a diagonal matrix is very simple. And also I minus H lambda is U I minus gamma lambda U transpose. And I minus gamma lambda is also simple because I just like subtract like 1 minus each one of the diagonal entries. So these are the things that you're going to show in your problem. I'm going to introduce the notation mu I is equal to Si squared. And so this is going to be mu1 squared divided by mu1 plus lambda up to L squared. Up to mu d divided by mu d plus lambda. And so, for example, so this is going to be gamma lambda, it's going to be diagonal. Mu I plus lambda. If you see my notation, if you get comfortable, this is like that. And then you also show that this I can use because the trace has this interesting property. Trace of h lambda squared, if I do that, it's going to be the same as the trace of gamma lambda squared. This you also prove using the circular property, this property that we talked about. It's a good exercise for you to use that. And so trace of a diagonal matrix is just the sum of the diagonal elements. So this is just going to be summation 1 up to n, these diagonal entries. So mu I plus lambda squared. So you can see how simplified that variance term becomes. Okay, so a little bit fast, but some of it you would show in your homework problems. Questions? Okay, one more thing. So let me basically we simplified the so we have this, we like have a nice expression for this guy. How about the first one? The first one, we note that this guy is really that psi applied to f star. Remember the psi like takes the samples. So psi of f star. It's 1 over root n f star x1 star xn. And we showed that like, if you apply psi to a function which is linear, this would look like that. So now I'm gonna have to deal with I minus h lambda psi f star. And so this is u I minus lambda u transpose psi f star. I'm going to call this C star. So what turns out to like these u's, these are like n by d. These are orthogonal. So x is n by d, right? And I'm writing it as u, which is n by d, times, I'm going to write it as like a d by d. So this is SV transpose. So what this is, if you remember a little bit of linear algebra, the column span of this and the column span of u are the same. So every column of x would be a linear combination of the columns of u, and the coordinates are like the coefficient of the linear expansion would be like the corresponding row here. So each row of this gives you a linear combination of columns and produces the columns of x. So the column span of x is the same as column span of u. The column span of x is basically the space of functions that can be represented by the basis that you chose, sort of, if you remember the feature map business. So u is spanning the same. So what I would like you two guys think about is that each column is basically a function, like samples of a function. And this is like a transformation of those functions so that the functions are orthogonal. So it's like a different set of functions. So I'll show you if you choose a polynomial basis. So this column would be 1. This is x, this is, let's say, x squared. These are going to be like still polynomials, but they're going to be now like normalized and orthogonal to each other. So u's really span the same sort of, I would say this is a little bit like function in space, the same function in space as the original data, but they're not orthonormal. So this is saying, this is also like the samples of the function. This is like basically saying, so if U is like, the columns are U1 up to UD, U transpose is going to be U1 transpose, UD transpose. So UD transpose psi of F star, this is like the samples of F star. So this is really U1 transpose psi of star up to UD transpose psi of star. So I'm projecting, or like taking inner product of the true function with the basis, these basis elements. And so this tells me like how much like component I put on each of the basis elements. So this has a lot of meaning. So this quantity that I define QC in RD tells me exactly which of these eigenvectors contribute to constructing F star. So for example, QC star 1 is very large, the rest are very zero. The first I'm calling eigenfunction, or the first U matters. And you'll see that S is basically going to be usually decaying. So the first so that this one, the first one is going to matter most. So I forgot to mention that S is usually ordered. So these S's are ordered so that S1 is bigger than S2 is bigger than SD. So usually the largest one is the more important component. So this has a lot of meaning. I might come back to it. But in any case, we define this, even if you don't follow the meaning that much. It's not very very critical. So I have defined this C star. Now, if you look at this, this is just the bias is I H lambda psi F star norm squared. So this is going to be U I minus H gamma lambda U transpose psi F star. I've called this QC star. And the interesting thing is that now I can also drop this. And I get this very simple formula. Why I can drop that? Because ux squared for any x would be ux transpose ux would be x transpose u transpose ux. This is identity would be x transpose x, which would be x squared. That's the advantage of having this orthonormal columns. Okay, so I drop the u. This is like some big x. And that's that. Let's call this A if you want, to avoid confusion. Okay, so I simplified this, and this is a diagonal matrix. It's like diagonal times QC star 1 up to QC star D. So when you multiply a diagonal matrix by a vector, just each diagonal gets multiplied by the corresponding element. So once the dust settles, this thing is going to be easy for you to verify that this is just going to be summation I minus gamma lambda, the entries are this. So you get 1 minus mu I plus lambda. These are the elements of the diagonal matrix times QC star squared. And this simplifies to summation I from 1 to n lambda divided by mu I plus lambda squared Ci star squared. Okay, so that would be the final result. And unfortunately, it took us an entire day to arrive here, but that's the result. So expectation of f hat lambda minus f star s squared is equal to summation I from 1 to n lambda mu plus lambda squared Ci squared plus sigma squared over n. Remember this, we simplified. This is the one that I sort of plug in here. That's our calculation from before. So you'd get this summation mu I or mu I plus lambda squared. So this is our final result. It looks very simple. It's not very simple, but like you can see the SVD sort of simplifies the argument a lot. and you get something which you can stare at and analyze. Okay. So what matters is like these mu i's are SI squared, and you can actually show that these mu i's are in fact the eigen values of that sigma hat, the sample covariance matrix as well. So how the sample covariance matrix decay. So these are the eigenvalues. I believe this is another homework problem. Using the SAD, you can show that these are also the eigenvalues of this. So the eigenvalues of the sample covariance matrix matter, the lambda, the regularization parameter matters, and how the true function interacts with these basis functions, with these like orthonormal basis functions, because Kc is like the inner product of these basis functions with that. And then the noise, that's the noise level. You can see the noise sort of appears sigma squared over n, which is usually what you expect. The training data and the noise level sort of interact, so you get sigma squared over n. And there's a lot that we can do with this. In particular, we can actually plot this, simulate things. What I wanted to show you guys, which we had to postpone to the next lecture, is to actually simulate and verify that this formula actually matches what we observe in practice, and also analyze what happens, for example, in terms of, so you can easily see that if I set lambda equal to 0 here, the first term is going to be 0. Only I have the second term, the variance. If I increase lambda, I'm going to increase the first term, which is increasing the bias. I'm going to decrease the second term because lambda is here. So if I increase lambda to infinity, this is going to go to 0. This is going to go to infinity. So I'm increasing the bias, reducing the variance, vice versa. So it gives you a very nice device to trade off the bias and variance. It's very similar to the bandwidth in the Nadaria-Watson case. So next time we're going to come back. We're going to do some simulation, plot this, and I'm going to argue, like, tell you what happens. For example, if you have high noise levels, if you have like what happens with overfitting, stuff like that, we can analyze using that. Okay. Yes.
What's that symbol at the end of the yellow text? It's like A transpose.
Oh, these are all like all A.
Oh.
A transpose A, which is norm A squared. Just changed everything to A. Sounds good. Okay. Any other questions?